Hello everyone, welcome to today's episode of The Art of Science and Controversy. As you can see, this is very different from normal. Reason why is I'm starting a new series, which is called Scientific Article Dump, where I just dump a whole load of information onto you about various articles and topics I've read of for research. If I am posting an episode of this series, that means that I have contacted people to interview and have either been rejected or just no one responded, and I don't want to put this information to waste. Which is why it's called a Scientific Article Dump, this new series, and the acronym for that is, of course, S.A.D. Because I am sad, we are sad, but at least we have this series, S.A.D. So, what am I going to be talking to you about today? I'm going to be talking about a hole that exists in physics, specifically what happens when you form a black hole, because that's a very interesting topic. And when you form infinite densities and infinite masses, what happens is physics isn't built for that. It breaks down. You get logical errors and contradictions, like, for example, the most famous contradiction would be the theory of relativity, general relativity, and quantum mechanics. They do not agree when you get to these masses and pressures. So which one budges? Do either budge? Do you get a new theory that needs to take over? That is what I'm going to be exploring today. But what is also a mystery is what happens just before you get to those pressures, just before you form black hole and all of physics breaks down. How do we explore those pressures just before you form black hole? By analyzing the densest and most extreme forms of matter that you can possibly have, which is where you enter neutron stars. Neutron stars are what I'm going to be talking about today, because research into the core of a neutron star at the end of the day is really research into matter's last-ditch effort to exist. It's research into how matter falls apart and breaks down, falling into itself. So, how am I going to talk about a neutron star? I'm going to first introduce what a normal star is, how it works, and then what happens as you add more and more mass, and eventually get this densest object that is possible before you form a black hole. That being said, I have 7 pages of material here, a 7-page script. I do not want to memorize all of it, and so I have not, and I will be constantly looking down and referring to this script. In the future, if you guys like this series, I will of course start to memorize these scripts and do a more professional quality edit at the end of the day. But we'll see what happens with this, and if it does, if you guys do like it, I will start to make more professional content out of it. For now though, I am quite literally just dumping information onto you. So, what is a normal star? How does it work? What holds it up? A normal star can be compared almost perfectly to a balloon, where in a normal star you have gravity crushing everything inward, just like the rubber of the balloon would try and crush the air inside of it inward. What opposes that? Well, that would be the thermal pressure of particles wiggling around. For example, in a balloon, you have all these particles and atoms, molecules bouncing around, and that creates an outward pressure opposing the rubber. Exact same thing happens in a star, and that is caused by heat, thermal pressure. So for example, if you put a balloon in a refrigerator, it literally will shrink down as you have less of that bouncing around of particles. Heat is just movement of particles. So how do stars generate this heat in order to produce this thermal pressure? That is where you enter fusion. Fusion was first realized that the fusion of hydrogen into helium would be exoergic, meaning it would produce energy and release the heat energy, in the mid-1930s by Hans Bethe. Stars can do a lot more than that, though. They can fuse much heavier elements than just hydrogen into helium, although that is their main source of energy, but they can also fuse elements like nitrogen, carbon, and oxygen. The chain reaction that leads to hydrogen being fused into helium is known as the proton-proton cycle. The chain reaction with carbon and nitrogen would be the CN cycle. If you add oxygen to that, you get the CNO bicycle. So there are all these different things happening in different layers of the star, all at the same time. And the main energy source of that star is switching between these different cycles as it ages. So, what happens as that star burns through its fuel? It changes its composition. It goes from being mostly hydrogen to having more helium and then denser and denser elements as well. As it does that, the helium would sink in the lighter hydrogen, forming a core of helium with an outer sheath of hydrogen. And with sufficient pressure, this helium core would begin to fuse as well via the triple alpha process, forming even heavier elements in that process, which in turn would sink again and form a new core of those elements. So, as this continues, you get more and more layers generated, with new cores being generated with each of these processes. And what happens is you have more and more layers over top of that core, exerting more and more pressure on an increasingly small and dense core. The fusion now occurs in ever-shrinking layer along that boundary layer of the core and those innermost layers. There will over time be not enough pressure in that layer between the helium and the hydrogen to generate fusion, and so fusion will begin to halt in those upper layers and just be concentrated around the core and those innermost layers, with only convective currents to carry that heat out to the outer layers. And so what happens is these outer layers begin to cool off, whereas the core of the star begins to get hotter and hotter and hotter as you have more fusion in effectively a thinner surface area, a smaller surface area around that core. And so as these compositional changes occur in the star, you get changes in the amount of heat energy being released and the balance between this gravitational pressure and this force from thermal energy. And that can actually be seen if you look at a chart that describes the binding energy of nucleons. You can look that up, and I'll actually put all my resources and citations in the description for this video as well, so you can look down there for it. You can actually see the amount of energy released by each of these fusion cycles as you take these elements and fuse them to form the next, how much energy is released by that. And you see after you go from hydrogen to helium, you begin to get a decline. So you have a lot of energy produced in the beginning, and then as you get heavier and heavier elements, that begins to plateau until eventually you get to iron. And you see that when you do get to iron, it actually begins to come down. Iron is at the peak of that, which means you can only release energy from fusion until you get to iron, element number 26, and after that it actually consumes more energy than it produces. And so the largest stars are able to fuse up until iron and no further. You cannot fuse past iron in the store of a car. In the core of a star. There, that's better. Now, this star has been fusing and fusing and fusing, and let's say it's a really large star and it's fused all the way down to iron. Now you have thin layers of fusion in the boundary layers between these elements near the interior of the star. And these outer layers, there's very little fusion happening there, so they cool down. But this inner core is still getting hotter and hotter and denser, and so it expands, and that thermal energy pushes those outer layers up, and they bulge out, yet they're also dimmer because they themselves are cooler. And so, you're now entering the red giant stage of the star's life cycle. Now, the mass of the star at this point will determine how it ends. So, for small stars, those outer layers which have been pushed out farther and farther from the core of the star might actually just drift off into free space and leave you with the core, which would be a white dwarf, which I'll talk about more later. Now, in larger stars, that supernova may actually occur. You hear about supernovas all the time, so what are they? A supernova is when under these pressures and temperatures you have these iron nuclei in the star's core, and those can't fuse anymore. If they do start to fuse with enough pressure, they'll actually consume energy. And so that's what happens. You have this process which is now consuming a lot of energy instead of releasing it. And so, as that energy is being consumed, there's not enough thermal energy to push outward on the star and keep it supported against gravity. And so the core actually collapses, as there's just not energy being generated to push against gravitational contraction. And that collapse increases the density of the core, which increases the effective gravity and gravitational pull of that region. Now, at a certain point, that core collapses to a certain density that is so great that the electrons in the atoms are actually forced into the protons of the nucleus, as you have electron degeneracy pressure collapse, which I'm going to talk more about later as well. This gives you a hard, rapidly spinning ball of neutrons, which simply cannot collapse any further. And so you have this collapsing occur, and then it suddenly stops. But those outer layers of the star are still falling down on top of that core. So what you have happen is those outer layers hit this hard ball of neutrons and rebound off, creating a massive shockwave, and that is what gives you a supernova. That shockwave rips through the star, blowing off all of the outer layers and leaving you with just this spinning ball of neutrons, which is now the core. So, as you can see, there are two outcomes to a star's death. You have either a white dwarf form, or you have a neutron star. So what are these objects? Well, a white dwarf will form if the remaining amount of material after the supernova is less than 1.4 solar masses, which is known as the Chandran-Sakar limit. So, if the amount of mass is between 1.4 solar masses and about 2 solar masses, then you have this neutron star form when those electrons actually merge down with the protons in the nucleus. And if the star is even greater than about 2 solar masses, the remaining core will have a black hole form. So let's compare white dwarfs and neutron stars before we get into the territory of black holes and the breakage of physics. So, a white dwarf is held from collapsing by electron degeneracy pressure. And this pressure is the result of Pauli's exclusion principle, which says that no two electrons with the same spin can occupy the same energy state in the same volume. That sounds really complex. It's just law words to say that you can't have two electrons in the same spot at the same time. Mostly just common sense. Now, due to this, as the atoms are put under increasing pressure by gravitational contraction, the electrons are forced into higher and higher energy levels of those atoms in order to not be overlapping with one another and defying Pauli's exclusion principle. In order for them to have higher energies, in order to not overlap and be in those higher energy levels, they need to travel faster and faster. Now, this means that with enough pressure, all the available energy levels are occupied in atom, and this is now known as a degenerate gas. And to quote the NASA website, for gravity to compress the white dwarf further, it must force electrons to go where they cannot go. Once a star is degenerate, gravity cannot compress it anymore because quantum mechanics dictates that there is no more available space to be taken up. So our white dwarf survives, not by internal fusion, but by quantum mechanical principles that prevent its complete collapse. So, to give you some figures on how extreme this object is, this white dwarf, the surface gravity is 100,000 times that of the surface gravity of Earth, on average. And the typical density of one of these white dwarfs is 10 million grams per cubic centimeter, which is 10 million times the density of water. Now, as NASA said, in order to compress the white dwarf further, you need to force those electrons to go where they cannot go. What does this mean, and is it possible? You have to first understand the reason they can't go to higher energy levels in atoms. That's because with enough pressure, they need to travel faster and faster, and eventually, with enough pressure, they'll need to travel at the speed of light. And they can't have more energy than that energy level because they need to travel faster than light, which is impossible. So, in order to obey Pauli's exclusion principle, they can't go faster to have higher energies. So what do? They cease to exist. Now that's a very strange thing to think about, but where do they go in order to cease to exist? Well, the electrons will instead be pushed down by this pressure into the nucleus of the atoms, and they will merge with the protons in there to form neutrons. That is what gives you rise of the neutron star I mentioned earlier. When that gravitational pull, that collapse, is even stronger than the electron degeneracy pressure that is preventing electrons from merging with the protons in the nucleus of atoms. Now, you end up with the electrons and protons merging into neutrons, and you now have a star which is essentially identical to an atomic nucleus, except instead of being supported by the strong nuclear force holding everything together, it's now supported by gravity. And this star would have an average of 20 neutrons for each proton, and a density on the order of 100 trillion times that of water. This star would consist of 3 layers, an atmosphere, a crust, and a core. The atmosphere would be just a few centimeters to meters thick and consist mainly of hydrogen and helium. The crust is a bit more interesting. It would be about a kilometer thick and consist of atomic nuclei arranged in a crystalline structure, with subatomic particles, specifically neutrons and electrons, in between the atomic nuclei. So the nuclei would form a lattice, a crystalline lattice, with these particles in between the nuclei. So I like to think of this, if you look up an image of the crystalline structure of salt, where you have these layers with sodium chloride in between, with sodium in between the chlorine atoms. And so that's essentially the same thing you have happening in neutron stars crust, except now that is made of atomic nuclei and subatomic particles instead of actual atoms. Now, below that crust you have the core, which is where you start to get into the mystery zone. It would consist of nuclei as well, but as you get deeper, the nuclei would grow larger and contain more and more neutrons. Eventually, these nuclei would actually spill over, and you get a soup of free-floating neutrons and protons. And then as we continue to dive deeper, we dive into the theoretical realm. So, the leading hypothesis at this point is that the neutrons and protons start to overlap with one another, and eventually you need to start thinking about this as being more of a soup of quarks, rather so much as a soup of neutrons. So, when you get this soup of quarks, you have some really interesting things happen, assuming you do get a soup of quarks. Now, what may happen is that soup becomes a superfluid, which experiences no friction and theoretically can continue to move forever once it's set in motion. That would happen due to the quarks' natural affinity for one another, as they could form Cooper pairs when under these pressures. This does some quirky, get it, stuff as far as the Pauli exclusion principle is concerned. That's because when you have these quarks pair up into Cooper pairs, they're no longer fermions. So a normal quark is a fermion. It's a matter particle. It's the same thing as makes up you or I. But the Cooper pairs now act as a single boson. A boson is a force-carrying particle, so it's like the electromagnetic force. It's like light. You can think of it like a photon. Fermions cannot pile on top of one another. You are solid. But bosons absolutely can pile on top of one another. And so what you happen now is these quarks, instead of needing to obey the Pauli's exclusion principle, are able to cram in incredibly close to one another, as they're no longer subject to the exclusion principle. And because they're able to cram in like that, they could form a frictionless superfluid, and that's how that would form. Now the same, or a similar thing I should say, could happen with neutrons, where neutrons pair up and create a superfluid as well, but that's not entirely certain, although to be fair, none of this is. So what evidence do we have of this superfluid forming? That is where we get into the realm of neutron star glitches and star quakes, which is really interesting. So, what is a neutron star glitch? A neutron star glitch is when you have the outside of the star, the crust, speeding up momentarily and then eventually slowing back down, all of a sudden, no warning. And so that's how it looks from the outside. And these star quakes only happen in pulsars. Pulsars are the exact same thing as a neutron star, except they're spinning incredibly fast, like tens and tens of thousands of RPM on average. And they spin so fast, in fact, that those magnetic fields they generate are strong enough to fling particles out into jets from the magnetic poles. These jets, as they form, create friction with the star's surface, causing the crust to slow over time. Now, we think that this star quake happens when the frictionless superfluid in the star's core eventually grows out of sync from that crust. And so now they're spinning at different rates, and these star quakes would most likely be when that superfluid imparts some of its angular momentum to the crust, causing the crust to speed up and the superfluid to slow down so that they're back in sync. Now, normally the crust is completely decoupled from the superfluid core, so why would they couple in the first place? Well, the leading theory is that the magnetic dipole of the neutron star would sometimes break, and that breakage of its dipole, its magnetic dipole, would exert a force, a torque, on the crust, causing it momentarily to couple with that inner core. So you'd have the two parts momentarily coupling, at which point they would resync, and from the outside it looks like that crust is speeding up momentarily. And that crust over time, over the course of days to years, would... My computer is doing funky things. Crap. I have a 28-digit long password and I entered it wrong. Why do I have a 28-digit password? Not for security, because it builds character, of course. Now, I left you on a bit of a cliffhanger. Over the course of a few days to years, that crust will actually slow back down and come back to its pre-glitch, pre-star quake rotational speed, and that cycle may repeat who knows how many times. This is now getting to the span of time that, well, we can't really observe these very long periods. There is, though, a second occurrence and body of evidence for superfluid in the core of neutron stars. In 2011, Danny Page and his team at the National Autonomous University of Mexico analyzed 15 years of X-ray emissions from a pulsar known as Cassiopeia A, which first became visible on Earth in the mid-17th century. What this means is it's quite a young neutron star, and so it's undergoing some interesting changes. At least that's what we seem to be seeing. So, what happens is that this neutron star is cooling down much faster than we would expect, and we can tell that by its emission spectra. Now, the prime explanation for this is that the neutrons in the core are constantly pairing up, breaking, repairing, breaking, repairing in a constant cycle in order to try and create a superfluid, a more stable superfluid. But in that process of pairing and breaking, they are releasing neutrinos, which then fly out from the neutron star and release energy, causing it to cool down. We should know if this is indeed what is happening in the next 50 years or so, once that superfluid has formed and is stable, at which point no more energy would be released, as there'll be no more neutrons being released and no more energy being dissipated. And so at that point it should cool at the predicted normal rate. Now, assuming the superfluid does exist, we don't know how much of it would be paired neutrons and how much of it would just be these paired Cooper pair quarks floating around. So, how are we going to test this? Well, we have an interesting experiment for that. So, Dr. Arzamanian from NASA is the lead investigator of the NICER experiment, which stands for Neutron Star Interior Composition Explorer. And it is a washing machine-sized box mounted on the side of the International Space Station. One of its key objectives is to analyze the radii and masses of various neutron stars, and to look at the proportionality, the radius versus the mass, on all of these different neutron stars. And this is useful for one simple reason. If neutrons exist in the core of a neutron star, they would act, in Dr. Arzamanian's own words, like marbles, creating a hard core, whereas if there are free quarks, they would create a softer and squishier core, allowing the star to shrink down. So, if the NICER experiment finds neutron stars with roughly the same mass but different radii, this could indicate a transitional threshold wherein those neutron pairs start to break down into that soup of quarks, allowing the star to shrink down. There could be, though, something even more interesting going on than just a boring superfluid in the cores of these stars. There could be something called strange quarks floating around. So, this gets us into the realm of hyperons. So, what's a hyperon? In your normal atom, you only get two types of quarks, the up and the down quark. There are, however, 6 total different flavors, as they're called, of quarks in physics. So you have the up and the down. You also have the charm, the strange, the top, and the bottom quarks. But those last 4 are too massive to exist in your normal atom. They're too unstable, and so they don't form. And if they ever do form, like in very high energy particle collisions, they only last for a split second before decaying down into more stable subatomic particles. It is possible, though, that these strange quarks could form from the up and down quarks in those extreme pressures of the neutron star. So, the top, charm, and bottom quarks are likely too massive to form even here, but if the strange quarks do form, that would result in mutant neutrons called hyperons. Or the quarks could, again, just float around freely in a soup. That's where the NICER experiment comes in to determine what exactly is going on there and where neutrons start to break down into this soup, if they break down into this soup. Either way, this does bring us nicely to the issue of using mass to look at the composition of neutron stars, because that mass can be useful for a lot more than just looking at whether the neutrons break down into a soup of quarks. It could also tell us the proportions of hyperons that could be possible if they exist at all. So, for example, Scientists used to think that up to half of the neutrons in a neutron star could be hyperons, but a star with this composition would not be able to exceed about 1.5 solar masses. In 2010, though, a team at the National Radio Astronomy Observatory led by Paul Demorest measured the mass of one neutron star to be 1.97 solar masses. Now, that eliminated a number of theories, and so the current estimate for the maximum percentage of hyperons that could exist in a neutron star is now just 10%, assuming they exist at all. So, why are we doing all these things? Why are we looking into the breakdown neutrons into quarks, into the possibility of hyperons? Why are we doing all this? That is where we come to the equation of state. So, an equation of state, if we're able to form one, would describe the state that matter would take under all possible conditions, and any neutron star would need to abide by this equation of state. Now, we know that neutron stars can at least reach 1.97 solar masses, but have we ever seen them at that lowest limit, the Chandrasekhar limit? Well, yes, actually. A neutron star merger was observed in 2017 when two neutron stars, about 130 million light years away from Earth, collided, and when they did that, they released gravitational waves. We had observed gravitational waves in the past, but never from neutron star mergers, always from black hole mergers, when black holes collide. So this was the first neutron star merger we had ever seen via gravitational waves, and it provided a bounty of information. First of all, we now know that each of those neutron stars was right around 1.44 solar masses, right around the Chandrasekhar limit. Which means that yes, you can have neutron stars ranging at least from 1.4 to 1.97 solar masses, and there may be more lying outside of those boundaries that we've not seen yet. And so that big difference in mass is really directing the equation of state and limiting the possibilities. So, as Jocelyn Reed, the co-leader of LIGO's Extreme Matter team, said, this is starting to make our equation of state thread and needle through these different mass observations. Trying to make compact stars work, as well as supporting massive stars, is getting to be very challenging for the theory. So we're getting closer and closer to having this equation that could describe any form matter may take, no matter the pressure exerted on it. And as we develop more and more sensitive gravitational waves detectors, we could look forward to even more interesting experiments with this sort of stuff, like detecting gravitational waves emitted by the swirling superfluid in the neutron star's core, which could flow in a pattern called an R mode and emit gravitational waves, which we would be able to detect. Now, all of our current technology is not able to detect these gravitational waves, but future upgrades to LIGO may be able to. And so to sum everything up, why are we looking into neutron stars? Why are we wanting to form this equation of a state and look at everything matter may be able to do under these pressures? In order to determine what is happening at that hole in physics. Will general relativity budge? Will quantum mechanics budge? Is there something new that we're going to need to make to take over at that point? What is matter's last-ditch effort to exist like? And that is what we're going to be finding out over the course of the next several decades. And I think it'll be very interesting. And some people think it may even be able to work with forming a theory for everything, as well as describing a theory of gravity and seeing what's going on with quantum gravity, stuff like this. So, I hope that you've enjoyed today's episode of The Art of Science and Controversy and all the information that I've given to you. Maybe I'll be able to find guests to talk and interview about this conversation, this topic with in the future, but right now it's not looking very promising, which is why I'm posting this. Fingers crossed. We'll see what happens. Do remember, if you're watching this on YouTube, you could always follow the actual podcast series on Spotify, Anchor, Google Podcasts, Apple Podcasts, all of the works at The Art of Science and Controversy. This will not be posted to the actual audio-only version of the podcast, though. This will only be on YouTube. And then clips of this you could find as well at Instagram and TikTok at TASAC, that's TASAC .podcast. So, I hope that you have enjoyed today's episode, and I hope you have a lovely day. Bye for now.